The objective of today is to give you a clear understanding when you're in front of your customer of what the questions you need to ask are, and the data that you need to glean in order to put a system together that meets your customers' design criteria and production requirements. It really begins with asking the right questions. You would want to consider that what we're doing is solving a problem by designing a solution. In order to do that, we need to gather the best and most accurate information that we can. With that information, what we're going to do is create a conceptual solution for the customer to solve his problem. And then once we present that solution in a conceptual format, if the customer agrees or after modification from the customer, we're ultimately going to develop the design of a system to provide the solution that he's looking for. The process always starts with the part. We need to find out from the customer what his largest part is, both size and weight. We also need to know what the smallest part is, both size and weight. Additionally, we need to understand the other parts in between the smallest and the largest part, both size and weight of those as well. And then what is that part mix? What percent of production is represented by each part? And the quantity of parts. Also in consideration is colors. How many colors will be applied? And then what's the composition of the parts? Is this a cold rolled substrate? Is it hot rolled? Is it wood, or is it plastic or some other substrate? So to get the answers that you need, what do you ask? Well, what's the part? What does it do? And what is the largest and the smallest, and what are their volumes? What's the material that the product is made of? What's the composition? This is important because we need to know if we need to pre-treat the product, we need to understand requirements for coating and things like that. So the composition of the product, what the product is made of, is very important. And also, what is the coating that we're going to be applying? Is this a liquid line or is it a powder line? What are the coatings consist of? Are they waterborne? Are they high or low solids? And really key is the cure parameters. What do we need to do in order to cure the product so we can handle them for assembly or packaging after the coating? And productivity. This is key in system design. How many per shift? How many of the widgets that we're coating do we need to coat per shift? And what constitutes a shift? Is it 10 hours? Is it 12? How many shifts per day? How many shifts per week? And then ultimately, how many weeks per year? I'm sorry, how many shifts per day? How many days per week? And then how many weeks per year? Also, what's the footprint or space allocated in the plant that we're going to be putting this system in? And really important is the budget. We need to understand what the customer has allocated for his project to get an understanding if it's feasible or not. Concerning the parts, to get a better understanding of what we need to do to completely process them, we need to have an understanding of where do the parts go? Are these under the hood of a car? Are these gas riser pipes that connect your gas meter to the transmission line? What are they doing? And what are they going to be subjected to? Are they going to be in a harsh coastal environment? Are they going to be subject to lots of UV from the sun? Are they going to be subjected to chemicals? What's the environment these products are going to be in that we coat? And what's their life expectancy? How long do you expect them to last? And it's always good to find out what condition the parts are before being coated. Are they heavily laden with soils that we need to remove either mechanically or with an aqueous solution? And it helps to know how they're currently being prepared. Is the customer currently having success with the process that they're currently utilizing, or do we need to make improvements on the product pre-treatment? When we talk about part size, this is showing a conveyorized product. When we talk about length, width, and height, these are where you take those measurements on the part to determine height, width, and length. Length, as we determine length, it is always the distance that the product is along the conveyor. Along the conveyor is always length. Height is from the conveyor to the floor, and width is always perpendicular with the conveyor. So our goal is to develop a solution. Here's an example of how we would go about that. We have a customer that needs to coat 300,000 parts per year. They have 240 available work days. They're a one-shift operation, and that shift totals 420 minutes. One shift is 420 minutes. The longest part in direction of the conveyor travel is 36 inches. We have to have some space between the products as well so we can coat and so they don't bump into one another during the process. So the clearance between products is 12 inches per side. This customer has 3 colors, 2 that are reclaiming. And we need to have an understanding of color change time if it's required. Here's how we would calculate, first of all, line speed. They have 300,000 parts that they need to coat. The parts are hung online on 4-foot centers. That is the part length plus the distance between the parts. That equals 1.2 million feet per year of conveyor space that they're going to need. Well, 1.2 million feet per year divided by 240 days, which is what they work a year, equals 5,000 feet of conveyor per day that these parts will take up. 5,000 feet is what we need to process the parts if it was a straight line conveyor. 5,000 feet per day divided by 420 minutes equals, which is how many shifts per day, is 11.9 feet per minute. So we have calculated that this line speed would be 12 feet per minute. Now, this does take into, this assumes that there's 100% yield, and we have not calculated anything in this scenario for color change or line gaps. It's 100% yield of their production requirements. But bear in mind, what we're doing here is just conceptually, first of all, putting together a conceptual solution for this customer. With that information, here is a layout that we could actually design for the system, for the customer, to give him a conceptual layout of what we would propose to meet his requirements. Now, sometimes we go through this exercise and sometimes we go through this exercise and we find that what the customer needs is a batch system. I'm going to briefly touch on batch systems because we are going to concentrate mainly on the engineered finishing solution here. But just quickly, if we go through this exercise and we find that we can't justify a conveyorized system, or the parts don't lend themselves to a conveyorized system because of size, then the solution for the customer is sometimes a batch system. What we need to take in consideration when they do fall to a batch system is the cycle time in each stage. We need to size the equipment to avoid bottlenecks. We need to make sure we have adequate room to load and unload the carts. In many batch systems, products are conveyed through the process on a cart. Some are done with an overhead conveyor that is moved manually with a shepherd's hook, but in many cases they are moved with a cart. When they are moved with a cart, we need to pay attention to the design and number of carts that we're going to have in the system. We need good density, just as we would on a conveyorized system. We need good part density so we are efficient in processing. We need to make sure that the parts are positioned and hung on the cart for easy and efficient coating and cleaning, because the parts will typically need to be pre-treated as well. And we need to make sure that they are hung in such an orientation that the parts don't hit one another when the cart is moved from process to process. Here's just an example of a manual push conveyor that you may utilize in a batch system. It's an overhead conveyor. The one pictured is an enclosed track, and you would move this with a shepherd's hook manually. A man would actually grab the trolley with the shepherd's hook and move it from process to process. On the right of this picture is an example of an I-beam, a man processing very large parts through a finishing system with the shepherd's hook. So we're from conceptual solution to system design. We've now provided the customer with a conceptual solution that he likes, and now we're going to get really precise with the system design. So how do we get there from the concept to design? Here's a typical coating system. You'll see there's a 5-stage wash system beginning on the left. Next to it is the dry-off oven. One thing we really need to consider after the dry-off oven is cool down time for the parts once they exit the oven, before they go into the powder coating, in this case, the powder coating operation. Once they go in there, they've cooled adequately and gone into the powder coating with powder applied. Then they go into the cure oven for curing. And then out of the cure oven, we again need cool down time prior to unloading the conveyor so employees can handle the product. So with an engineered system, we typically use continuous power conveyor. As shown in the previous example, we determined the line speed by the hanging pattern and the volume. In this scenario, now that we're designing the systems, we must factor in rejects, tooling changes, color changes, breaks, and etc. for production requirements. We also need to factor in future growth. Typically, continuous conveyors are of an I-beam construction. We have 3-inch, 4-inch, and 6-inch. The larger the I-beam, the greater the capacity per linear foot that the conveyor can adequately and safely process. So weight, when we ask for weight of the products to be or that are to be coated, that's not only for the design of ovens, and it is also for the design of conveyor. Weight plays a part in the design of systems from a conveyance standpoint, as well as any ovens that might be in the process, so we know the mass that we're attempting to bring to temperature. Again, this is an I-beam. We also have enclosed track conveyors, which is shown here. Enclosed track are typically for lighter weight products. They don't have the capacity of the I-beam. They don't have the weight capacity of the I-beam, but they're very good in their niche. They're very good products to utilize. This is just a picture of an I-beam conveyor that has products, large, heavy products that it's processing. One option that may be utilized is a power and free conveyor. Power and free conveyor enables a customer to index parts. He can move products and stop in each process if he needs to. These are typically utilized when we have space constraints, and we don't have, for large parts where we can't do a continuous movement because the length of parts, they're used in that scenario. And just when there needs to be longer process time, whether from a coating or whether from a pre-treatment or a curing standpoint, with dwell time at each station. These are commonly used in industry, but by and large, the I-beam and the enclosed track without power and free are what we deal mostly with from day to day. Another option for conveyor is chain on edge. There's a picture of the chain on edge, and it's good for products that need to be turned. Anything that you might utilize on a flat line conveyor, you can possibly use on chain on edge, and they're very good for their niche applications. One thing to consider on an overhead conveyor are the vertical curves. Now, sometimes because of floor constraints available to us in the plant, we have to go overhead or higher with some of the equipment. And when we do that, we have to raise the height of the conveyor in some areas. When we're doing that, we need to keep in mind that we need to minimize the degree of incline to avoid of loss or load space. And typical vertical curves are typically 15 degree, 30 degree, or 45 degree. Again, minimizing the degree of incline is very desirable. The lower the degree of incline you can utilize, the better off you are in preserving your line density. There's just a picture of, this illustrates load spacing and clearance as a product is hung on the conveyor and has to make the rise from the lower elevation to the higher elevation on the conveyor. Horizontal curves are equally important to pay attention to. Typically, radiuses are 2 foot to 8 foot. What we have to do in engineering is make sure that the largest part will make the turn without hitting or causing a loss of load space. Here's an illustration of horizontal curves, and one that's properly engineered. So we've developed, we've decided and chosen the appropriate conveyor for our customer. And now through the process, we start with hanging methods. So we've got the conveyor, and now we need to decide how are we going to hang these products to propel them through the process. Well, you can use wires, rods, fixtures, and chains. The thing to consider with your hanging method is the presentation of the part to the application equipment, which speaks directly to the coatability. Will the way these parts are hung, are we going to easily be able to provide coating to all of the areas that we need to? If it's an electrostatic system, the parts to be coated obtain their ground directly through the hanger. So it's extremely important that we design the hangers and the hooks to where they have a good contact with one another and with the workpiece to be coated. Another big consideration is stem length, hanging from the conveyor to the application area. We need to make sure that there's adequate stem length so we don't spray into the conveyor slot as we're coating the product, and thereby propelling powder outside of the application booth and also coating the conveyor. And a consideration on your hooks and hangers is how easily can we clean them? How easily can we remove the powder or liquid coating from them when it comes time to clean them? How easily can that be done? Again, some things to consider when you're designing your hangers are the presentation to coating and also washing. Can they be easy? Do they hold the part in such a fashion that they're easily coated? Grounding is very key. Hanger length is very key, so we maintain the powder inside the spray chamber, and drainage. If the parts that you're coating have to go through a process washer, we need to make sure that the parts are hung in a manner that allow the solution to drain. If you look at the illustration, you've got a beam that is hung at the top at the top of the illustration that's hung with no angle. Therefore, it can trap water and carry water from stage to stage in the washer or even outside the washer as it exits. The correct way would be to hang it on an angle as the illustration, the beam at the bottom of the illustration shows. Angle it so that water can easily drain utilizing gravity. When you design your hooks, there's some benefits to hooks. Hooks are inexpensive. There's some flexibility with them. You can hang them on various types of carriers through the conveyor, and they're easy to maintain. Generally speaking, you've got on the bottom left-hand side of the illustration, you've got a C hook and an S hook. Typically, a double bend hook provides a better ground point than a full radius bend. The full radius bend is on the right hand, the S hook, and the double bend hook provides a better ground because it takes the weight of the part and that's hung on it and distributes it in a smaller area than the S hook would. Therefore, with the weight, it has the potential to provide better grounding. Custom-made racks. The benefit of custom-made racks is accuracy. You can get great line density, and you can also, if you customize racks for your particular application, you can design them, especially in an automated system, where they are presented to the automatic guns in an optimum fashion, which also would provide you consistency. Custom-made racks lend themselves to great density, and that's a key for efficiency on any finishing line. Is the more metal or wood or plastic we can get per square foot on the conveyor and process effectively, obviously the better off we are. Custom-made racks do provide stability. There's when they're custom-made, it's stable from an application standpoint, where the racks typically don't move as much in process, and the benefit is high yields in production. Output is also optimized with the custom-made rack. Here's a nice example of racking. The line density here is extremely high, and it's a very efficient. They're coating their parts in a very efficient manner. Now, some people are sometimes concerned with the cost of racking. Here's a scenario that gives people an opportunity to consider the cost. We have a scenario where a customer has a line speed of 8 feet per minute. The rack spacing is on 2-foot centers. Throughput, we have 8 feet per minute times 60 minutes equals 480 feet per hour. 480 feet per minute, it should be hour. 480 feet per hour divided by 2-foot centers equals 240 racks an hour. Well, the house racks that this particular customer developed, it was 240 times 200 pieces per rack equals 480 pieces an hour. With a special tool rack, 240 times 4 pieces a rack equals 960 pieces an hour. So you can see by bringing in somebody to help the customer design a rack, this customer was able to double their production just by the utilization of a rack. Here we spoke about racking earlier and hangers and stability and the strength and stability of racks. You can see here, this is unstable racking. It's hung from one point. The hooks, as you can see from the illustration, are bent. There's no consistency or very little consistency from hook to hook, and these hooks do not optimize this customer's line. From the previous scenario, we had house racks, 2 pieces a rack, special tool, 4 pieces a rack. You can see the benefit there in this illustration. Here's just another picture of dense racking. The dense racking equates to this customer to high output and better transfer efficiency. We've got more product in front of the powder cloud in this case than we would if there was more space and more air between each product. So this also increases the transfer efficiency and product utilization for the customer as he applies his coating. Now, pre-racked parts provide an opportunity for a customer to rack his parts offline. You can imagine from this illustration how difficult it might be for a person or a crew to load this line and unload the line as it was moving. That's the reason that we will pre-rack parts offline. If you're going to be processing many small parts and you're going to be utilizing racks like this, in system design, we need to bear in mind that they're in the footprint of the system, we need to allocate some space for not only loading and unloading the line, but pre-racking parts as well. sometimes we have to coat parts that require masking. So when in considering part masking, we have to look at, well, what's effective to mask this part? What's the cost per mask? Do we remove the masking before or after cure? What would be best in our process, and what would be required in our process from a part standpoint? Can you use it more than once? Is it a one-time utilization and then thrown away, or can it be used many times? And can the mask be cleaned? There's several types of masks. Here's some illustrations of them. High temperature tape. We have caps, plugs, tubing, and die cuts. These are there are many suppliers that supply masking to the finishing industry, and many of the options are reusable, and many of them are cleanable, used every day in production throughout the country. So now we have chosen the conveyor, we've determined how we're going to hang the parts, and we've also determined how we need to mask. So now we're going to process the product through the finishing system. So here's what we need to consider as we're hanging the part. On each side of the part, as it's going through the profile opening, whether it be a washer, whether it be a paint booth, liquid or powder, or an oven, we need to maintain a 6-inch clearance around that part from the profile opening. So from the bottom of the opening to the bottom of the part, we need a 6-inch clearance. And from each side of the part in the profile opening, we need a 6-inch clearance. And from the top of the part to the top of the profile opening, we also need 6 inches. What's very important, as we spoke about earlier, is the stem length of the hanger. We need 27 inches minimum from the bottom of the conveyor to the top of the part as it's propelled through the processes. That's very important. So when we're designing our product, our system, this is how we design the profile openings to these standards. So we've loaded our line now, and we're going to design a process washer. If your customer is currently utilizing a chemical supplier, if they're currently washing the product, it's a very, very good idea to get in touch with their chemical supplier. While the customer can tell you and will tell you information about the chemicals that they utilize, getting confirmation from the chemical supplier is always a very good idea. When we're developing a new line, we need to ask things like, well, what are the number of stages that we're gonna have? What's the temperature of each stage? What's the dwell time in each stage? And we need to consider the parts, both length and carry out, when sizing the drains between stages. Typically, when we design a drain between a stage and a washer, the minimum size that we will make those drains is equal to the length of the longest part. However, when a part has carry out, because of the design configuration, the geometry of the part, we need to know that, because we need to be able to make the drains longer so we don't contaminate one stage to the next. It's very important that we get this information. Also, we need to know the chemistry that's going to be involved in the process washer, whether it be a zirconium, whether it be an iron phosphate. Knowing the chemistry is key in us knowing what we need to construct our pumps of in the washer and the tanks, whether they be stainless steel or not. After we wash, we have to dry the product off. One thing we have to consider as we dry off is, do parts cut moisture? Most companies will do the very best that they can to hang their parts so that the parts dry. But the parts drain and therefore they don't cut. But there's some product configurations that there's no way around it. You just can't help but that the part's going to retain some moisture through the washer. So what we have to do is address that issue, and how that's done is it's done in several ways, or maybe in all of the ways, is that we elevate the oven temperature in the dry off. We could make a longer oven or a larger oven where the dwell time is longer for the part, or we can use blow-off equipment, which is compressed air, clean compressed air, that would force the cupped water off of the part. Sometimes it requires all three of those scenarios, sometimes just one. What's very important to consider in the system design of your line when you're going to dry the part is adequate cool down prior out of the dry off oven and prior to the coating application. So we have to have adequate time built into our design so that we have the proper temperature part at coating, whether it be a powder line or a liquid line. Cure oven, we need to pay attention to the weight of the part and understand what the load's going to be, a full load in the oven, so that we can engineer our oven with the appropriate burner BTUs to get that to raise that product to the temperature it needs for cure. We need to understand the continuous operation of the oven. If continuous operating temperatures are 500 degrees Fahrenheit or larger, we will need to incorporate a stainless steel burner box into the oven design. If it's below 500 degrees, we will use standard aluminized steel for the burner box. So the goals when we're going to design a system for a customer: number one, keep it simple. Just do the best you can to minimize the moving parts and keep it simple for your customer. Number two, make sure it fits the building. We've got to have an understanding of the footprint as well as the height of the ceiling where we're putting this system in, to make sure that what we engineer and what's required to be engineered for the part size, it can fit in from not only the floor plan perspective, but also the height perspective. We need to build the product for the task. Again, as an example, are we going to be continually heating or continuous using the oven, use of the oven for cure at 500 degrees or better? If it's a water, we would need, at that point, we would need to manufacture pretreatment. If they are, that requires a stainless steel washer. We have to understand what the task is and build the system according. And we need to focus on value instead of cost. What's the value of providing the solution to the problem the customer's having? This is capital equipment, and there is a cost involved, and a full finishing system can cost a lot of money. But what's the value? What does that bring in terms of throughput? Help the customer with the return on investment and find out, the value of this product instead of just the cost. If at all possible, and if the customer has been realistic, keep within the budget. Do what you can in engineering, do what you can in process to minimize the cost of the system without sacrificing quality or sacrificing the objective, but do what you can to help the customer keep within his budget. Be complete. Cross all the T's and dot all the I's for the customer. Make sure we've accomplished the task and we've left no stone unturned in terms of helping him out. And be sure, lastly, be sure that you build in flexibility for the customer for the future. We don't want to design a system for today's needs, ignoring what he might need 3 to 5 years or 10 years, maybe even 10 years down the road. We need to build him something that can serve him now and into the foreseeable future. So that's a quick overview of system design and some of the things that we take into consideration. I've put together 2 scenarios that feel free to run through these with me, and it can help you grasp the concepts as that we've discussed today, or that I've talked about today. We're going to review the first line speed calculation that I made at the first of the presentation, and after that we'll go through two scenarios quickly to show again with new information in each scenario to demonstrate how line speed is calculated. So remember earlier, we had 300,000 parts per year, a customer needing to quote 300,000 parts per year. He worked 240 days per year. That was a 1-shift operation per day, and that shift consisted of 420 minutes. Longest part in the direction of the conveyor was 36 inches plus a clearance of 12 inches. Number of colors was 3, and he wanted to reclaim 2. So the line speed calculation, based on the customer's part, the parts would be hung on 4-foot centers. 300,000 parts per year would take up 1.2 feet of conveyor per year. 1.2 feet per year divided by 240 days equals 5,000 feet per day. 5,000 feet per day divided by a shift of 420 minutes equals 11.9 feet per minute, or a line speed of 12 feet per minute. Again, this assumed that this was an assumption that it was 100% yield and no additional factors for color changes or line gaps. Now, when we're engineering a system, we use this calculation for a conceptual solution for the customer. When we move into actual system design, we typically calculate 10% more of conveyor needed for a system design, and that's what we'll do in the next exercises. We'll incorporate 10% more calculated for color change, things of that nature. So what do you ask? We have a customer that builds mini bikes and go-karts. So what do we ask? We ask, what's the part? What does it do? What's the largest and smallest in volumes? The material composition, the metal, is it metal or multi-metal? What's the coating that's being applied, whether it be liquid or powder coating? And what's your productivity needs? How many per shift? What constitutes a shift? How many shifts per day? And how many days per week? And then how many weeks per year? And what's the budget? He makes, there's some images of the frames that we're going to powder coat as well as the go-kart frame. So here's the answers to the questions that we just asked. What is a part? What does it do? Well, there are many bikes and go-karts. Here's a list of the sizes. The largest is 30 inches wide by 12 inches tall by 42 inches long. We do 500 a day on an 8-hour shift. The smallest are pegs and small parts. It'll be gang racked, and the rack is 36 inches long. There will be 100 of those per 8-hour shift. Other size mini bike is a 24-inch wide by 10-inch tall by 36-inch long frame, and there's 200 per 8-hour shift. The material is cold rolled steel, mainly tubing, with multiple welds. The coating that we're going to apply is a TGIC powder coating, 95% black, and 5% being multiple colors. Productivity. Here's what we need to know. How many per shift and what constitutes a shift? 7.5 production hours. How many shifts per day? Will be 1. How many days per week? 5. And how many weeks per year? 48. Okay, we've got the answers to our questions. Now let's apply them and design a system. And his budget is $1.5 million. Space allocation is key as well, as we've already discussed. Here's some images of the typical part. So let's apply the information that we found to the calculator and the formulas. His largest part is 42 inches. When taking into consideration the distance between parts, we have 4.5 feet, and his volume per day is 500. On his smallest parts, which were racked, it was 36 inches plus the space between racks times 100. It's 4 foot times 100, or 400 feet. And then the mini bike, again, 4 foot times 200, a quantity of 200s equals 800 feet per day of conveyor. So a total is 3,450 feet of conveyor per shift. A shift is 7.5 hours times 60 minutes per hour. That equals 450 minutes per shift. 3,450 feet of conveyor per shift divided by 450 minutes per shift equals 7.66 feet per minute needed to process these products. Plus 10% that we just spoke about a moment ago. First time we've utilized this in our scenarios. 10% for rejects, downtime, color change, poor line density, power outage, or whatever. That brings the 7.66 to 8.52, or a total of 9 feet per minute for line speed to process the customer's products. That was an actual real scenario, and that's a layout that we designed for the customer right there based on the information that was given to us. Last scenario. Again, the questions that we ask. What's the part? What's the material? What's the coating that's going to be applied? Tell us about your productivity, and what's your budget for the project? Okay, here we go. Workshop number 2. What's the part? Well, we got wheels, largest, smallest in volumes. And there they are there. They range from 16-inch diameter to 20-inch diameter. There's going to be 500,000 of the 16-inch per year, 200,000 of the 18-inch per year, and 100,000 of the 20-inch per year. The material is cold rolled steel, and the coating being applied is a dual coat powder system. They have a primer, and then on their colors, they're 70% white, 10% black, and 20% multicolor. Productivity, here we are at, there are 7.5 production hours in a shift. There's one shift in a day. They work 5 days per week, and they work 48 weeks per year. They don't have a space allocation. They don't have a budget for this yet, but they have provided us the space allocation. So here is the application of the data. We're going to put these wheels on a chain on edge conveyor. If you'll remember, we have a variety of opportunities on types of conveyor that we can utilize. This part, it's all wheels, allows us to very efficiently utilize a chain on edge conveyor. And we're going to put them on a chain on edge conveyor on two foot centers. Bearing in mind we have 16, 18, and 20-inch wheels to coat. So we had to take into account racking on or utilizing the chain on edge with the largest part. So we had a 20-inch wheel with 4 inches for space between the wheels for coating. So we'll put them on, all of the parts will be on 2 foot centers. The volume of all of the wheels was 800,000 of the 16, 18, and 20. The total was 800,000, which translates to 1.6 million feet per year. So as we do the math, if we take 1.6 million feet per year and divide that by the 48 weeks that this customer works per year, that equals 33,333 feet per week. If we take 33,333 feet per week and divide that by 5 days per week, we get 667,000 feet per day. If we take the 6,667 feet per day and divide that by 7.5 hours per shift, that equals 889 feet per hour. If we take the 889 feet per hour and divide that by 60 minutes per hour, we come up with 14.8 or 15 feet per minute. And that's a picture of our wheels being coated on the flat line. An hour is very difficult to get all of this information. I know out in a manner that is easy to grasp. I mean, I've been feeding you guys with a fire hose. I know that. As Jennifer said, we're open to questions now at this point. If you have any, I'm happy to answer any and all. And at this point, I'll turn it back over to Jennifer to moderate the questions.
Thanks, Scott. Yes, if you do have a question, you can type it into that question box in the GoToWebinar control panel. We'll just wait a few seconds to see if anyone has any questions. don't see anyone typing anything. You can always, if you have any additional questions, you can always email myself, jegan@colmetsb.com, or Scott, which is sjones@colmetsb.com, and we'll be able to help you, or call customer service and they can connect you to Scott. If there's no questions, we'll go ahead and dismiss the webinar, and we thank you for taking the time to attend, and you all have a great day.
Thanks, everybody, for your time and letting me spend some time with you today. I appreciate it. Thank you.
Thanks. Bye-bye.